Now we'll see locking protocols. Two-phase locking protocol. Sir, why we require that protocol? Simple locking mechanism we can use, right? Whatever we have learned so far. So the problem with that I will tell you, so that we can go for this two-phase locking protocols. The problem with general mechanism without rules, if you simply or blindly if you put the locks, then you can't achieve concurrency. I mean, you can achieve concurrency, but you will have problems. We will see one problem first of all. We know that this is unrepeatable read, correct? So read of a, write of a, let's take again read of a. So there is a problem with this. What is that? So when you read two times, because since in between it is updated that a, then you can't read same thing two times. That is unrepeatable read problem, correct? So this kind of schedule should not be allowed according to conflict serializability. So I mean conflict serializability will not allow it. See, read to write, write to write, read. So there is a cycle. That's why this is not conflict serializable schedule. So conflict serializability is going to avoid it. And we also know that it is bad schedule, but we will see whether our locking will I mean I can say accept it or not. We will see. Easily we can accept under locking mechanisms. What I do is I lock transaction t1's database variable item a using shade of a. After that I unlock it. See the series of locking mechanisms: shade of a, unlock of a, exclusive lock on a. Now it will be successful, then I do unlock of a. Now after that, shade of a, unlock of a. So without any protocol, any rule, if you simply use your locking mechanisms, then what happens? You see, you tell me first of all, shade of a is successful or not? Yes, successful. Then immediately read of a will be done. Then you are releasing it. Then what can happen is your transaction T2 might get chance to get executed under your CPU, and it might issue exclusive lock on A, and it will be successful, right? Then you do write of A, then you will release it. Then again your transaction T1 will get shade lock and read of A will be performed again, unlocking will be done. So what is big deal here? So finally your locking mechanism is allowing bad schedules. Then why to learn locking? That's why. So simple locking mechanism will not work, but this locking is a basic building block to achieve concurrency and I mean to avoid the concurrency control problems. For that we have to design protocol. Systematically we have to keep the locks, not in a random way. So this is random way. So basic 2PL is a systematic locking mechanism. We will see that. So what is basic 2PL model? I will tell you. In basic 2PL, every transaction should follow this rule. That is, it can lock any data item at any time, not a problem. So every transaction is going to take some locks. That means they are going to achieve some locks. Then after some time, at any time if you release, that means one transaction, I am talking about T1, let's say. If T1 unlocks a data item A, further T1 cannot lock any data item. After that, no locking can be done. Try to understand this point. No locking can be done. So for every transaction, once unlocking is done for any database item, then other lockings, I mean after that no locking can be allowed. That means some students understand it in a wrong way. Sir, if T1 unlocks database item A, T2 also cannot lock. It is independent of, I mean, this rule is for everyone separately. That means T1 unlocks any database item, it cannot lock further. Similarly, now T2 can lock, but T2 unlocks any database item, something B, then after that it cannot acquire any lock. In that way, there is a systematic way you have to acquire. What is that? You can acquire it any time. T1 can acquire any number of locks. But once it releases one lock, then after that no more acquisitions. Similarly, T2 also, it can lock any number of locks, any number of variables. But once it unlocks any database item, then after no further locking can be done. Your DBMS will simply reject that. So that means what? Every transaction has to lock first, after that unlocking. There are only two phases, I can say. That's why it is two-phase locking protocol. Every transaction will see in this model two phases. One is locking phase. That means we here in this phase, it's a logical idea, that's it. Really there will not be any design like this, like one one particular border, like physical bordering like this, like 9 o'clock to 5 o'clock locking, 6 o'clock to 10 o'clock unlocking. This is not in that way. So what I'm doing telling is it's a logical split. So you can imagine a logical split where, so transaction T1 here is locking so many variables, might be, depends on its situation. So it's like lock. Suddenly it unlocks one thing, then after that only unlockings can be done, no further locking. That's why you will see two phases, one is locking phase, second one unlocking phase. Similarly T2 also can lock for any number of times, but once it unlocks, then no further locking. So in simple line I can say that in 2PL every transaction, once it unlocks any database item any database item, it cannot further lock any database item. Understand? Once unlocking is done, no more locking. So that is basic 2PL protocol. So we'll see one transaction, otherwise one schedule, and we will try to achieve locks using basic 2PL, and we'll take a bad schedule. We'll check whether really basic 2PL allows bad schedules. We know a lot of bad schedules, right? So unrepeatable read problem, temporary update, dirty read, everything is bad, right? We'll take one such kind of bad schedule and we will see whether basic 2PL allows it or not, right? So that we can understand the capacity of 2PL and the acceptance of 2PL, right? We will see that. Now we'll see given schedules, like how this locking is going to be executed and whether, so a schedule is as it is allowed by locking or not. Before that I would like to tell one point. Generally when there is interleaving, because of that interleaving there might be problem, there might not be, correct? So how can you say that given interleaving is good or bad? For that we have theoretical foundations. What are they? Serializability, right? That is conflict serializability, view serializability. But you remember one thing. So this is, already I told you one thing. These are all possible serial schedules, all schedules, not serial, but all schedules, which are serializable. That means they can have same effect as serial schedules. But your conflict mechanism was able to find out only few. And your view serializable mechanism also going to find out few. So view and conflict serializability I can show using Venn diagram like this. Finally, these are all, this outer circle if you see, that covers all possible schedules which are good. Good means they can be serializable. Serializable is different from conflict serializable and view serializable. So every conflict serializable schedule is serializable. Every view serializable also serializable, but there are still some serializable schedules which cannot be caught under CS and cannot be caught under view definition. That means there are some interleavings or concurrent transaction lists, otherwise concurrent schedules. They might be good, but your conflict and view definitions were not able to find out whether they are good or bad. Okay, so however we can't, now you tell me. So we know only two things, what is conflict serializability, second one view serializability. Using that somehow we were able to find out something good or bad, but we are missing something here, right? So however we don't have option here, let's leave it. In the real world also same thing. So when the life goes on, then sometimes you pick up some things by deciding, like example, let's say suddenly job. When you have this dilemma to take job or not, you are in that situation, let's say, then if you take job you get salary and you get some commitments and discipline, everything, right? So shall I take job? At least you get money, so definitely you will take it and you say that that is good decision sometimes. So let's say you are going for gym. Is it good or bad according to you? Let's say because when you go to gym, then it will be healthy for you, like you will become healthy and fit, then gym is good. In that way, somehow using your consciousness you are finding something good or bad. So let's say I can say, let's say drinking poison, yeah, not good. So somehow you are deciding it, but there are some things which you cannot say good or bad because your consciousness, otherwise whatever the knowledge you have, that is not sufficient. I will tell you that kind of examples. Let's say you are doing Facebooking. So when you do Facebooking, so maybe your network will be improved and you might see some status messages, and that improves your knowledge, and sometimes you get some good links. Because of that you might get some knowledge. But at the same time, the same Facebook can spoil you, right? You know that. So now finally, should I do Facebooking or not is the open question, right? We don't know. Then search kind of thing, this one. So sometimes we are not able to find out whether some schedule is good or bad, then leave it. So we don't talk about them. At least now we'll talk about schedules which can be accepted under conflict serializability and view serializability. Okay, so most of the time, so we focus on conflict serializability. So let's do that. The reason is, so in theory, I mean generally also, conflict serializable schedules are easy to detectable. That means we can easily detect them within polynomial time. Already I told you, within order of n square time, even I can check whether some set of schedule, some schedule is conflict serializable or not. It's computationally inexpensive. That's why the conflict serializable schedules are popular generally, but of course doesn't matter for us. So what I want to tell you here is, this locking protocol, whatever I introduced now, just now, that is 2PL. Now what I am going to do is, I will try to compare my 2PL's capacity with this conflict serializability. So there is a close relation between conflict serializability and this 2PL. That's why first of all what I do is, I just take a schedule and I will try whether it is conflict serializable or not. Then I ask locking protocol, my dear locking protocol, this is not conflict serializable schedule. That means conflict serializability, discarded it. Now what is your turn? That means now it's your turn. Tell me whether you accept it or not. In that way we are going to relate conflict serializability and this one 2PL. So conflict serializability is for me a benchmark to say that conflict serializability accepts some schedules. They are good. Definitely they are good. Now we'll ask 2PL, do you accept it? So in that way we are going to compare, I mean, a real-time implementation versus theoretical idea, right? So we'll do that. So here I take one bad schedule according to conflict serializability. See, read to write, write to read, there is a cycle, right? So it might be, I'm not saying that it is bad schedule, sometimes it may be good schedule, but your conflict serializability doesn't know that, okay? So, but however we know that, I mean, forget about this conflict serializability. According to our understanding, we have seen some of the famous problems, right? This is repeatable read problem, unrepeatable read problem, correct? So this is actually bad. Even conflict serializability also says that it is bad, right? So, but I would like to tell one point. So conflict serializable schedules allows only good schedules, but conflict serializability, if it does not allow something that may be good, may not be good. Remember that point. That is enough. Now we'll see this one. So there is a cycle. So according to conflict serializability, so that concept has a doubt on this schedule. We will see whether locking allows it or not. Let me do locking now. 2PL locking. Recall what is 2PL locking? We lock. First of all, we try to lock whatever we want, because once we unlock any data item, after that we can't lock it, correct? So we will see that. So there is only one database item for simplicity. So now if this, as it is, this to allow the schedule, that let's say this is 9 o'clock, this is 10 o'clock, this is 11 o'clock are issued. Then at 9 o'clock to achieve read of A, before that we should acquire shared lock of A. We don't need exclusive lock. Now this is the latest point. We can't, further we can't acquire shared lock here. The reason this operation read of A is done here, this is the earliest point where we can acquire shared lock, right? Now sorry, it is latest point. So after this we can't acquire, right? This is the best point. Now similarly, since we are doing read of A here also, then the earliest point we can release A is only here. In that way I am trying to reduce this holding of lock. I can start locking here, I can unlock here. But sir, why don't you do this one? You unlock here and then immediately start locking here, so that this T2 also gets chance to acquire the lock. But that is not idea of 2PL, right? In 2PL, so acquire release is not possible. Growing phase followed by shrinking phase. And one more thing I have forgotten to tell you. So in 2PL, so what we do is, because we know that there are two phases. First of all, we lock. Suddenly once you unlock, you can unlock anywhere, but once you unlock, then only unlocking can be done but no further locking, then automatically you get this kind of picture. See, initially 0 locks and you acquire a lock, acquire a lock, acquire a lock, acquire a lock, but suddenly if you release a lock 3, then keep on releasing. That's why, so you see this kind of growing phase of locks followed by shrinking phase. In the two phases, first phase is growing phase, second one is shrinking phase. Now here, so after unlock you can't lock it further, we know that. That's why, so this is not possible, then this unlocking is not possible. So in this between you can't unlock anywhere. Why? If you unlock anywhere, then you can't further lock. So that's why this is the safest point or earliest point. That's why I told you earliest point where you can unlock A, correct? So if that is the case, and then this is the unlocking point, then how right of you can acquire the lock at this 10 o'clock? Not possible, right? So we'll try to request Mr. Read of A. Read of A, you want shade lock of A here, right? But I want here exclusive lock. Please release here somewhere. But if you release here, you can't get it back. That's why. So 100% I am sure now. So this schedule is as it is, cannot be executed. So if you try to execute under your model, did you remember locking model? So what happens, I will tell you. So one possibility is, let's say T1 acquire shade lock. After the time proceeds and T2 gets chance, and T2 will try to acquire exclusive lock on A, but it is unsuccessful and T2 will be blocked. Up to what time? Up to this 11 o'clock. When at 11 o'clock unlocking is done, then your T2 will come back and it will try to achieve again exclusive lock, and it might get successful, and here it is going to do right of A. Try to understand. So now the question is, this schedule, this is now modified schedule which is allowed under 2PL, but not as it is when your T2 has right of A in between read of A, read of A. So your 2PL protocol accepts the schedule by modifying it. That's why if in the gate question, if they ask this schedule is allowed or not, it is not allowed as it is. But after moving right of A to here, it is allowed. That will be taken care by your protocol. Understand? So 2PL does not allow it. Similarly, we see this one here also. So it is not conflict serializable schedule. You see, read to write, T1 to T2, read B to write B, T2 to T1. So whether it is good or bad, I don't know, but it is not definitely conflict serializable. So already I told you, a schedule is not conflict serializable, then still it might be good, might not be. We don't have any reason whether it is good or bad, right? But if a schedule is allowed under conflict serializability, it's definitely good. Now we will see such schedule. Let's call it is a schedule which is not allowed under conflict serializable. At least we try to allow under 2PL. Whether it is allowed under 2PL or not, we'll see. For that, here read of A, correct? But here T2 has right of A. So we plan locks because we just see the possibility. We don't know how DBMS will lock, but we will try to imagine a possibility. Is there any possibility for DBMS to acquire the locks? We'll try as a human being. Now, so read of A. Here we can keep shade lock, right? Now, so since this T2 wants exclusive lock on right of A, before that we should release it, right? So what I do is, so I will see the what is the maximum point where I can hold this shade lock up to this point. After that we have to release it, otherwise T2 cannot acquire. So I am just writing unlock of A here, but once I unlock, I cannot further lock, but I want one more lock. Then see, we have to do locking of B before unlock of A. So I do here exclusive lock on B. So this is the best point where I can do locking of B. The reason, if I do locking here, then I will be controlling unnecessarily others, correct? So here if I lock here, then what happens, we'll see. So now at this point your T2 can take the lock which is exclusive lock of A. The reason, we already released it. Now let's continue. Here you want shade lock on B, but already there is a shade lock on B, correct? Then you can't acquire. Understand? So you will be blocked definitely. Now just remember, T2 got blocked on what? T1. Now, so time continues. Then when time proceeds, the point comes here. After some time T1 gets, this right of B, but already it is acquiring exclusive lock on B, correct? So it can definitely perform this operation and it will eventually unlock B also. When it unlocks B, then this T2 will be released and it will continue doing this read of B, correct? But when it will be done, see, so this read of B will be postponed to this point. So this will be moved. Write of A will be done, but read of B will be postponed. Now this is the postponed schedule. If you see, read of A, write of A, write of B, read of B. So there is no conflict order. That means there is no cycle. Otherwise this is conflict serializable schedule. So finally what I want to say is your 2PL protocol is also allowing only conflict serializable schedules. So that is what my intuition. But we can easily prove that 2PL locking allows only conflict serializable schedules. I will show that later, but at this moment just this is the way we can achieve locks. So finally here and here we were able to achieve the locks, but after extending or after moving the instructions, you remember it, as it is this schedule and as it is this schedule was not allowed under 2PL, remember it. Okay, now we'll see this statement. Every schedule which is allowed under basic 2PL is conflict serializable. Really it is correct statement. Then a schedule which is not conflict serializable should not be allowed under your locking mechanism, correct? So really let's say there is a schedule that contains some transactions T1, T2, T3. What we have to prove is if a schedule is not conflict serializable, then it should not be allowed under basic 2PL. Then only the statement is correct. So let's take such non-conflicting serializable schedule. So definitely it will have cycle on some transactions, correct? Let's say in very big schedule, these are the 3 transactions which are having cycle. I don't know about other transactions, just leave them. So students might ask this question, sir, why 3 transactions? Why not a cycle on 2 transactions? You can do that also. We can prove for 4, 5, anything. So for just, I'm not assuming the length of the cycle. It is one cycle. So when you have this cycle, so we focus on unlocking points. That means, so really it is allowed under, I am assuming initially that it is allowed under locking mechanism. That means 2PL. Really it is allowed. Then let's focus on T1. Mr. T1, you have some database item. That means you are going to read some database item or write, and same thing T2 also going to do. Otherwise some conflicting thing T2 is going to do. That means if you read A, then T2 is going to write A after you, right? If you do write A, then T2 is going to do either read A or write A, correct? So you people have some conflicting operation. Then my question is, Mr. T1, when are you going to release the first lock? I don't know when are you going to release A, leave it. But when are you going to release first lock? That is called first unlock, right? So after first unlock only, you are going to release other locks. After that, you never acquire the lock. Recall this basic 2PL. Once unlocking is done, no more lockings. That's why I would like to know what is your first unlocking point. So T1 said, I am going to release my first lock at 9 o'clock. Remember, this 9 o'clock is very important time for us. At this point, your T1 is going to release its first lock. After that, no further locking, remember it. Now we'll ask T2. Mr. T2, since the first unlocking is done by T1 at 9 o'clock, then you have to take its resources, right? That means some variable will be released by T1. You have to take it and you have to acquire the lock on it, correct? Then it will be definitely after 9 o'clock. Why? Since the first unlocking itself is done at 9 o'clock, then how can you acquire that lock before 9 o'clock, right? You can't, right? So the conflicting operation, if even that at 9 o'clock T1 releases the conflicting lock, still it requires to acquire it and it has to release. What I want to say is T2's release of first lock will be definitely after 9 o'clock for sure. My simple statement is T2's first unlocking will be done definitely after 9 o'clock, not before 9 o'clock. The reason, even T1 is releasing its first lock at 9 o'clock, but T2 wants a lock on a database item which is which is now used by T1 and which is locked by T1 and it is going to release after 9 o'clock. Then definitely T2 is going to use it definitely after 9 o'clock and it is going to release it, and we forget about when it releases, but we'll just ask T2, Mr. T2, what is your first unlocking point? So definitely it is after 9 o'clock, let's say 9 o'clock 10 minutes. Now since T2 and T3 are having conflict operation, then T3 is going to use a variable which is already locked by T2. For the T2 has to release it. The first releasing is at 9 o'clock 10 minutes, then other releasings definitely will follow, but we don't know when it is. So that's why I can say that I don't know that T3 is going to acquire a lock which is released by T2 definitely after 9 o'clock 10 minutes, because that is the the earliest time. The reason T2 is releasing its first lock itself at 9 o'clock 10 minutes, then maybe if that lock which is released at 9 o'clock 10 minutes is the log, I mean the variable which T3 wants, then maybe at 9 o'clock 10 minutes immediately it can hold the lock, but after some time it has to release. Then we can safely assume that the releasing point is 9 o'clock 20 minutes. So what we do is, since we are following first unlockings, that is sufficient. So T1 is first unlocking at 9 o'clock, T2 is unlocking at 9 o'clock 10 minutes, T3 is, let's say, unlocking at 9 o'clock 20 minutes. Then there is a relation between T3 and T1. What is that? T3 has a variable which has to be given to T1, right? So T3 is now holding locks, first unlocking at 9:20. So T1 has to take the lock from T3, because which is released by T3, because there is one conflicting operation. So that conflicting operation, let's say right of B. Okay. So here T1 also is having operation right of B, right of B, right of B is a conflicting operation, but in the schedule T3's right is first, after that T1, that's why there is an edge. Now you tell me. So currently at 9:20 is the earliest point where your T3 is releasing the locks. Then when lock on B will be released? Definitely after 9:20, otherwise at 9:20. That is the earliest time, correct? So definitely T1 has to acquire the lock for that this B after 9:20. Let's take earliest 9:20. Immediately, let's say the lock is acquired by your T1, then 9:20. But already we know that first unlocking is done at 9 o'clock. How can you lock it at 9:20? Correct? So this is a problem. So whenever there is a cycle, then we can prove that, see, 9 o'clock is first unlocking, 9:10 is first unlocking here, 9:20 is first unlocking. Then with same concept, here 9 o'clock 30 minutes should be the first unlocking, but already we know that 9 o'clock is the first unlocking. Then where is the mistake we are doing? Why are we getting this contradiction? Because our initial assumption is wrong. That is, so whenever there is a cycle, so we thought we can allow it under 2PL. To allow it under 2PL, definitely this is the unlocking times, 9 o'clock, 9:10, 9:20, again 9:30. Then you get contradiction. That means whenever you get contradiction, I can say that this argument is wrong. What is that? By assuming that we can lock it under 2PL, we cannot lock this schedule under 2PL. So finally, whenever there is a cycle, so you get this kind of contradiction. That means unlocking and locking cannot be done using basic 2PL, because you are getting contradiction, right? So that's why finally I can say that a schedule is not conflict serializable. Definitely it is not allowed under basic 2PL. So same thing I can tell like this. Every schedule which is allowed under basic 2PL, that's why it has to be a conflict serializable. That is what final conclusion, and we proved it, right? Though I have taken a 3-length cycle, you can extend it to any length cycle. So generally no one teaches you proofs, but if you know this kind of proofs, and that will improve your understanding. So don't skip this kind of proofs. So suddenly when you go to IITs for interviews, example, let's say you did not get sufficient rank to directly get the admission, then probably you might have to attend the interview. So when you go to interview, they ask this kind of fundamental questions, like, where you need a proof to, argue something. So simple arguments will not work for them, correct? So we have to give the proof. That's why learn this kind of proofing techniques, at least whenever someone teaches you. Understand? So finally you understand that whenever you have a basic 2PL, so that will definitely allow what? Conflict serializable schedules. Yes. So we have one protocol which can be implemented, right? So the problem is this basic 2PL is, so see this problem, so you can understand. In this schedule, so you have read A, write B, write A, read B. Let's try to allow it under 2PL. So since it is a non-conflicting serializable schedule, see, read to write there is a conflict, and T2 to T1, see, write B to read B there is a conflict, there is a cycle, of course. So it should not be allowed under basic 2PL, and definitely it is not allowed. We proved it, right? A schedule is not conflict serializable. It cannot be allowed. We know that. So, but your DBMS doesn't know initially. It will try, correct? So when it try to achieve locks on these operations, what happens? We'll see. So we are just seeing one possible scenario. One possible scenario is your DBMS might lock your database item A on shared mode on behalf of T1. Let's list it out. So now currently database variable A and the owner who is holding it T1, right? So we know that, did you remember that avail matrix? So availability, who is availability is 1 now, the lock mode is shared, that's it. Now after that, so we remember this one, like, so whenever there is a operation write of B, so whenever there is a write of B, so B is now free, then that will be marked, that means now availability is busy, so exclusive mode, right? So far this one and this one both are successful, right? So T1's read and T2's write. Now see the story. After some time, so you will come to this point where T2 is issuing write of A. For that we have to try exclusive lock on A. Your DBMS will try it. For that it will go to, first of all, A, it will see avail 1 and the mode is shared, but shared and exclusive is conflicting. So what happens? This locking, that means your T2 will be blocked first of all, and this operation will be postponed. We know that, correct? So this operation. So slowly what happens? So time comes for T1, right? T1's read operation, read of B. So here your DBMS will try to issue shared lock on B. Whenever S of B is tried, first of all your DBMS will come here, since it is what? Availability is 1 and the mode is exclusive. Exclusive versus shared incompatible, immediately, so the transaction will be blocked, T1. So now T1 is blocked, T2 is blocked. So your DBMS is waiting and these transactions also waiting for others to release it, correct? So at this moment I can say that if these are the only two transactions in the system which are related to database items A comma B, now see, both are blocked. Who will release T2? Definitely T1, but T1 is also got blocked. Who will release T1? Definitely T2. So I can say that T1 is waiting for T2 and T2 is waiting for T1. So there is a chance of getting deadlock. So basic 2PL suffers from deadlock. That means it might get deadlock. So how to avoid it? So we have, however, deadlock detection and prevention algorithms. We will study them. So in real-time implementations, what they do is, so they take 2PL protocol and we have actually deadlock prevention algorithms. The combination of locking protocol, and whenever we get deadlock, to prevent it, we have some algorithms. I'm going to teach, however, the combination people use to, finally to do the locking. So we'll see that later. So there are two famous algorithms for deadlock prevention, that is wait and die algorithm. Second one, wound and wait. So we'll see that, however, but here I would like to do something here. That means, can we avoid deadlock without that deadlock prevention algorithms? Do we have any locking protocol which automatically eliminates deadlock? Yes, we have. That is called conservative 2PL. So it's a variation of basic 2PL. We will see that. Now we'll see the technical problems with this conservative 2PL. It is very difficult to implement. So why it is very difficult to implement? To understand, see this scenario. You have two transactions T1, T2, and T1 is doing read of A and write of B eventually. So according to conservative 2PL, we have to lock this database variable A and B at a time. Assume that, let's say, we have instruction in high level, that is locking A comma B at a time. So assume one high level programming language like Java, it has an instruction to lock all the variables at a time. So we imagine like that. So there is a S of A instruction, X of B instruction. Whenever you call them, automatically variables will get locked and all the information will be updated. Okay, but it is easy to understand that. So this instruction will be taking more than one machine instruction, correct? So these are all high level instructions. You know that every high level instruction is converted to machine instruction, correct? Without that we cannot execute, because finally your processor is going to execute machine instructions. That's why these high level instructions, which looks like, let's say this is only one instruction, but end of the day this is converted into hundreds of machine instructions usually. So Sir, what happens if there are multiple machine instructions? So assume that let's say you are taking two machine instructions to do this activity. One machine instruction, it need not be true generally. So but let's assume like this. So to do shared of A, that means to acquire all that lock. Otherwise we know how to acquire that lock, right? So many things we have to do. That entire process takes one machine instruction, and this entire process of exclusive lock on B can be done by machine instruction 2, then still you cannot implement this conservative 2PL. Why, we will see. Assume that let's say there are two machine instructions. Okay, so they are, let's say, one for acquiring shared lock on A, one for acquiring exclusive lock on B, right? So we are doing using two machine instructions, M1 comma M2. So meanwhile what can happen, T2 also has, let's say, read of B, write of A. For that, really T2 is also following conservative 2PL. So I'm just telling the instructions what it requires. It also has to do, exclusive lock on B, sorry, shared lock on B, whatever it is. Let's take otherwise write of B. So it requires exclusive lock on B and exclusive lock on A. Since each lock can be acquired by at least one machine instruction, that machine instructions, let's say M3 comma M4, right? So finally four machine instructions are required, two for this and two for this. Really conservative 2PL is executed. What happens, we'll see. At 9 o'clock, since we are in a computer where context switching is allowed, you can understand this context switching and everything only if you know operating system clearly. So this is your processor. So every program is executed by processor, correct? Assume that let's say at 9 o'clock you are executing this instruction. Your processor is executing this one, shared lock of A. Let's say once it is done, let's say it's successful. Assume that everything is available. So this will become 1. Understand? Then there may be a situation where your operating system has decided to take the transaction T2 for execution. If that happens, then X of B will be executed. Then see, that's why. Now see, effectively we are not locking all the variables at a time. We are holding some lock at this point, right? T1 and now control moved to T2 because of operating system properties, right? So T2 now achieves exclusive lock B. Will it be successful? Yes. Then it will make 1. So this instruction is done. Now assume that it is round robin link scheduling. So in a computer, if round robin link scheduling is executed, then some period of time transaction T1 will be executed and some period of time transaction T2 will be executed. Then again imagine that T1 gets turned. If T1 gets turned this time, so machine instruction 2 has to be executed, that is exclusive lock on B, but it will become unsuccessful because it is already available. Then we know that T2 gets blocked, correct? Sorry, T1 gets blocked here under B. Now after that, let's say eventually T2 gets turned and it will try to acquire remaining lock which is on A, then exclusive lock of A will fail and T2 will be blocked on T1. Again you are doing the same thing. You are holding the lock and trying to acquire another lock. That should not happen. That's why if you take two machine instructions to do this thing, then in between interleaving can happen and same thing can happen and deadlock will come. To avoid the deadlock, we have to implement this conservative 2PL such a way that there should not be a gap between these two. That means between two machine instructions always there will be a gap. That means between these two machine instructions your processor can decide to take any other job. We should avoid it. For that we have to make this entire instruction as one instruction. And remember one thing, our computers are designed such a way that when you are doing one machine instruction, without completing that machine instruction, so no one can take control from your program. Understand? So that's why it will work. For that, finally I will tell you in high level what we have to do is, somehow we should find out a machine instruction which can do locking A and locking B with one machine instruction. If you do that, what happens, if really your computer executes your instruction, both variables will be locked, otherwise none. In that way we can achieve conservative 2PL. But unfortunately what happens is, example, your transaction T1 is very big and it requires, let's say, 100 locks, because it requires locks on A, B, C, in that way 100 variables. Then we need to, there are two problems. One is unnecessarily you are locking all the database variables, so you are reducing the concurrency. others cannot acquire the locks. Second thing, there should be one machine instruction which can acquire all the locks with one single instruction. That might not be feasible. So machine level support you may not get. Second one, this will be leading to starvation. If you have very bad transaction like this, it is acquiring a lot of locks. Let's say if it is get successful, so if it holds all the locks by that time, then all the small transaction which need, example, see the situation. This is a very big fat transaction which got all the locks like A, B, C, all the locks now with this transaction. It is not going to release them unless it completes its complete set of operations. So meanwhile, what can happen? Small transactions might come like T2, T3, T4, which are very small transactions. Very small transaction means it has only one variable to be modified. Maybe it is doing write of B, another transaction is doing write of C, another transaction is doing write of D. So all these transactions are waiting for this transaction to be completed, but it's very big transaction. Whenever small transactions wait on very big transaction, then we say that it is a starvation. Why it is starvation? They never get chance. They get chance very rarely. Correct? If this transaction releases it, then only you get chance. So I can say that these small transactions will stop. Similarly, fat transaction also will have starvation here. How we will see. See the situation. You have very big transaction called T1. So what T1 is doing, we will observe. So T1 is going to do some write of A at the end of the day at 9 o'clock in the night. Okay. In the early morning, let's say 6 o'clock, it is going to start its set of operations. Assume that at 6 o'clock it is doing something write of B. In between, it is doing some other stuff, very long transaction. Sometimes in your database, you might have this kind of transactions, very long transactions, right? So which scans all the database, that kind of things. We don't know, whatever it is. So see, this kind of transaction is there. Then if you apply a conservative 2PL, then what happens? We have to acquire all the logs at before we proceed, correct? Assume that it is accessing 100 variables, then you read 100 logs. Now in your system there are some other transactions which are very small. Every transaction needs only one log, like this transaction requires B, this transaction requires C, this transaction requires D. They are slowly coming into the system. But at any time, if you see, all the locks are blocked by T1, correct, in the early morning, and it will release at night. Then what about these people? So they get starvation. Now finally, when you have a big transaction, because of that, smaller transactions can get starvation because of conservative 2PL. Is it not inefficient? You are reducing the concurrency. Easily we can see that, correct? At the night 9 o'clock, you need some operation. For that you locked it in the morning. It's so unfair, correct? So that's why I can say that this method is unfair. Second one, at the same time, smaller transaction also can stop bigger transaction. How you see? Consider the situation where T2, T3, T4, they all came into the system at 9 o'clock in the morning. Almost everything came at 9 o'clock, and each and every transaction requires exactly one lock or almost one lock. Example, let's say A, B, C, D, every lock is acquired by the smaller transactions. Now our big transaction T1 came and it wants all the locks at a time, then it cannot get it. Eventually T2 will release it, but still it cannot get it. So T3 will release this lock, but it cannot get it. In that way, after releasing all that locks by these transactions, so what happens is suddenly T1 again will try to acquire all the locks. Meanwhile, what can happen is one more small transaction can come and quickly it can acquire a lock, something D, correct? Then again T1 cannot get all the locks. That's why, so when you are trying to lock all the 100 locks, and if you have competition from other transactions which are very small and they want only one to win, but you want 100 locks at a time to win, who will win? Most of the times, the smaller transactions can get success, but not bigger transaction, correct? In that way, in this model, so either smaller transaction, if once T1 gets all the locks, then smaller transactions will get struggle, and if all the smaller transactions gets locks, then this bigger transaction never gets chance. In that way, so each and everything will get starvation, bigger and smaller. So that is the problem with conservative 2PL. Generally we don't implement this model. because there are so many reasons we have seen, right? So what we do is, that's why, what is the purpose of this entire thing? To avoid the deadlock, right? So what we do is we go for basic 2PL, otherwise other locking mechanisms, followed by deadlock prevention algorithms if you have deadlock. That's it. So I will be teaching what is deadlock prevention algorithm later. At this moment, just remember that we have deadlock prevention algorithms. Okay.